Design of concrete beams based on T-beam. This is used in conjunction with either one-way or two-way slabs. Sections consist of the flange and web or stem. The slab forms the beam flange, while the part of the beam projecting below the slab forms is what is called web or stem. We have a one-way slab. It forms a T-beam, the slab and the beam, also in two-way slab. And analysis of flange sections. Floor systems with slabs and beams are placed in monolithic pour. Slab acts as a top flange to the beam, which is T-beams and inverted L or spandrel beams. The L shape or the spandrel beam, and this is the T-beam with a slab and a beam. And for the positive and negative moment regions in a T-beam, the flange at the connection or the joint of the beam will have cracks at the flange area, while the cracks at the web or stem is at the midspan of the beam. If the neutral axis falls within the slab depth, analyze the beam as a rectangular beam, otherwise as a T-beam. So we have the depth of the slab. Once the neutral axis is at the depth of the slab, and we will design as rectangular beam. But if it falls within the depth of the slab, we will design as a T-beam. So we have the height of the total height of the beam and the effective depth from the center of the reinforcement bars up to the top fiber of the slab. And we have the B or the flange width and the thickness depth of the slab. And to find the effective flange width, portions near the webs are more highly stressed than areas away from the web. In this case, we have B from the center line span 1 and the center line at distance or span 2, and the total distance is the B or the flange width. However, the effective flange width is at this point up to the other side, and this will be B sub E. And how to find BEF? B effective is width that is stressed uniformly to give the same compression force actually developed in compression zone of width B or the actual. And this is the actual B and the effective B. And for ACI code provisions for estimating B effective, T beam flange, B effective is less than or equal to L over 4 or less than or equal to 16 HF or the height of the flange plus BW. B effective is less than or equal to L over 4 or less than or equal to 16H of F plus BW or less than or equal to B actual, whichever is lower. And for inverted L-shaped flange, B effective is less than or equal to L over 12 plus BW or less than or equal to 6HF plus BW or less than or equal to B actual, which is equal to BW plus 0.5 times the clear distance to the next web. And for isolated T-beams, HF is greater or equal to B over BW all over 2, and the effective B is equal less than or equal to 4 BW. And for various possible geometries of T-beams, we have the single T, which form a T shape, twin T, and to analyze, we will combine the width of the base 1 and base 2, and that's the total BW, and this will form a T-beam. And for the box, we will combine the BW left and BW right, and it will form 2BW. For analysis of T-beam, we have case 1. A is less than or equal to h of f, or the height of the flange, same as rectangular section. Steel is yielding under reinforced. Assume that the strain of steel is greater or equal to the strain of yield. And F sub S is equal to steel is equal to F sub Y, or yield stress. And check for A that is less than or equal to H of F. The effective B flange width is equal to, and the thickness T, and the depth, or the effective depth D, from the center of the reinforcement bar up to the top fiber of the slab. And we have the base width BW. The distance A and the centroid is along or above the bottom base of the slab, and that's C. And we will find the value, or check the value for A. And in this case, we have A is less than or equal to height of the flange. And for equilibrium, tension is equal to compression. A, which is equal to A sub S times F sub Y all over 0.85 FC prime times B effective. And to calculate the nominal moment, m sub n is equals to a sub s times f sub y multiplied by d minus a over 2. For case 2, we have a is greater than h of f, and we assume that the steel yields. C of f is equals to 0.85 fc prime times b minus bw multiplied by h of f. And CW is equals to 0.85 FC prime BW times A, which means that the neutral axis is below the depth of the beam, which is at the web portion of T-beam. And we have the distance C. And T is equals to A sub S times F sub Y. And A sub SF 0.85 FC prime times B minus BW multiplied by HF all over Fy. And the flanges are considered to be equivalent to compression steel. T is equals to C sub F plus CW A, and it is equal to A sub S minus A sub SF multiplied by F sub Y all over 0.85 FC prime times BW. We need to confirm that A is greater than H of F, wherein C is equals to A over beta 1. And the strain for steel, it is equals to D minus C all over C, and it is greater or equal to 0.005. To calculate the nominal moments, m sub n is equals to m sub n sub 1 plus mn sub 2, and mn1 is equals to a sub s minus a sub sf multiplied by f sub y times d minus a over 2, while m sub n2 is equals to a sub sf times fy multiplied by d minus h of f all over 2. The ultimate moment mu for the T-beam are given as m sub u is equals to theta times m sub n, where theta is equals to F multiplied by C over D for a T-beam with the tension steel yielded using function C over D. And for the lower limits, flange and compression, we have rho minimum is equals to A sub S all over BWD is equal to larger of between 3 square root of fc prime over fy or 200 over fy, whichever is higher. Flange in tension, A sub S minimum is smaller of, it should be smaller of 6 square root of fc prime all over fy times bwd, and it should be larger of 3 square root of fc prime all over fy multiplied by b effective times depth, or 200 over f sub y times b effective times d. If AS is provided is greater or equal to 4/3 of A sub S required based on analysis, then A sub S minimum is not required. Or theta m sub n is greater than 4/3 of mu for AS which is provided. Example: a T-beam for a floor system has a slab thickness of 100 mm and a total depth of 550 mm. It has a web thickness of 300 mm. The T-beam is cast monolithically with the slab. The beam has a simple span of 6 meters with a spacing of 2.4 meter center to center. The beam carries a live load moment of 163 kN-meter and a dead load moment of 84 kN-meter. Fc prime is equals to 20.7 megapascal. Fy is equals to 413.7 megapascal. Assumes steel covering of 65 mm. Then determine the effective width of flange. 2. Determine the depth of compression block. And 3. Determine the steel area required. So this is the T-beam with a thickness of 100 millimeter for the slab, and from the base of the web up to the area of the steel or the center of the steel area, we have 65 millimeter as covering or concrete cover. And from the center of the steel reinforcement up to the top base of the slab, that's 485 millimeter, and this will be effective depth and a total distance or height of 550 millimeter. First, determine the effective width of flange. Three options on how to find the width of the flange. First, effective width of flange. So letter A, B, that's
1/4,
of the span, and that's
1/4,
of the span, which is equivalent to 6 meter, or based on millimeter, that's 6,000 millimeter, and equivalent is 1,500 millimeter. Next, to find the effective width of the flange, we have the formula B effective is equal to B of the web plus 16 times thickness of the slab, or BW, that's 300, plus 16 times the thickness of the slab, which is 100, and the total BE is equal to 300 plus 1600, or 1600 plus 300, that's 1900 millimeter. And C, B sub E, is the spacing of the beam from center to center. So spacing of the beam from center to center, so that's 2.4 meter. 2.4 meter or 2400 millimeter, and that's B effective. Out of the three effective width of the flange, we will choose the lowest value for the B effective, and the lowest value is equivalent to 1500 millimeters. So the effective width of the flange, or BE, is equal to 1500 millimeter, and that's problem number 1. And number 2, determine the depth of compression block. So that's compression block. So depth of compression, so depth of compression block, we assume that the neutral axis is above or within the depth of or the thickness of the slab, 0.85 FC prime. And for the tensure, that's ASFY. And from the center of this steel reinforcement up to the centroid of the compression area, that's D minus A over 2. So let's find first the ultimate moment. So M sub U is equal to 1.4 moment of dead load plus 1.7 moment of live load. Based on the data, moment live load or moment dead load, that's 84 kilonewton meter. So 1.4 multiplied by 84 kilonewton meter plus 1.7 multiplied by the live load moment, which is 163 kilonewton meter, and moment or ultimate moment value. So 1.4 times 84 plus 1.7 times 163, and the total ultimate moment, that's 394.7 kilonewton meter. And we assume that the neutral axis is within the flange or the thickness of the slab. Mu is equal to theta times c times d minus a over 2, where theta is equal to 0.90 and c is equal to 0.85 fc prime of AB. And Mu, that's 394.7, is equal to 0.90 times 0.85 times 20.7 of A multiplied by the B effective, which is equivalent or the effective width of the flange, that's 1,500. And effective depth, that's 485 minus A over 2. Convert that 394.7 kilonewton meter, convert that to Newton millimeter, or multiplied by 10 times 10 to the power 6. And simplify. So 394.7 times 10 to the power 6, based on simplification, 16,616.67 is equal to 485a minus 0.5 a squared. Using the quadratic equation, a squared minus 970a plus 33,233.34 is equal to 0. Using the quadratic equation, we have two values of a, and we need to find or check for the positive value. That's 35.57 millimeter, which is less than 100 millimeter, which is the thickness of the slab. So therefore, the depth of the compression block A is equals to 35.57 millimeter. That's number 2. And to find the steel area, number 3, steel area C is equals to T, which is equivalent to C is equals to 0.85 FC prime AB, and equate that to ASFY. So that's 0.85 times 20.7 FC prime, and the value for A, which is the depth of compression block, that's 35.57, and multiplied by the effective width of the flange, that's 1,500 millimeter, and equate that to A sub S, and multiplied by the yield strength which is 413.7 megapascal. 413.7 megapascal. And AS is equal to, so multiplied 0.85 times 20.7 times 35.57 times 1,500, and we divide by 413.7, the value for steel area, that's 2,269, and in millimeter squared. So this is the steel area required.